Hopefully you can see it now in full mode. Okay, so I'm José Lizares, a PhD student from University of Santiago de Compostela, and today I'm going to talk about the sustainability performance of the superheated steam drying technology, and I'm going to show to you a preliminary life cycle assessment that we made under the framework of the SteamDry project. But first of all, I would like to provide some context on why these technologies are relevant from the sustainability point of view. So as you well know, drying stage in the industry is highly energy intensive, and not only for paper making, which it accounts for approximately 70% of the total energy consumption, but also this is relevant for other sectors like food and wood. So as you well know, with the European Green Deal, with the objective of net zero emissions by 2050, we are going to face stricter performance benchmarks, and also in parallel, we expect that the European allowances prices will rise. If now we are paying around 78 euros per ton of carbon dioxide equivalent emitted, we expect that in 2030 we are going to pay around 150 euros. Maybe a little bit less, but of course this price will be higher for sure. So in this context, it becomes essential to develop technologies with low carbon footprint. And this is precisely what we aim to demonstrate in the SteamDry project. Using the life cycle assessment methodology, we don't only evaluate the kilograms of carbon dioxide equivalent emitted, but also other broader environmental impacts of this technology across different impact categories, as I'm going to explain today. So to demonstrate the environmental benefits of a new technology under development, we need to focus on what differentiates it from previous solutions or currently technologies used in the industry. So for this reason, our analysis concentrates specifically on the drying unit and the energy sources that are used to power this process. However, what we observed in the literature manuscripts in which they apply life cycle assessments is that most authors adopt a broader system perspective, and they include under the analysis the upstream and downstream processes. This is illustrated, as you can see in the slide, by the bar charts, which shows the number of studies between each boundary configuration previously made. So as you can see, for example, only 2 studies applied the life cycle assessment methodology focuses specifically to the drying stage. And other 8 studies, the gray bar, used non-standardized frameworks to quantify the carbon dioxide emissions. So the application of this life cycle assessment methodology is quite a novel approach for drying technologies in the paper sector. So this life cycle assessment methodology is standardized under ISO 14044, and its application is basically divided into 4 clear steps. The first one is defining the goal and scope. That means choosing the functional unit to which we will refer all the environmental impacts. So in our case, this functional unit will be 1 ton of dried paper with 95% of drying content. And also in this step, we define the system boundaries that we are going to analyze, the scope. So we are only going to focus on the dryer. So this will be a cradle-to-gate analysis on the dryer. The second step will be the life cycle inventory. This is basically the data compilation. We gather and we identify all the inputs and outputs of the process under analysis. So in our case, for this, we used the results from the previous models presented by our project partners for both a conventional and a superheated steam multi-cylinder dryer. So just to remind you, our results showed a significant reduction in energy consumption and using electricity as the only energy input for the superheated steam. The third step is the impact assessment. So in this, we choose a calculation methodology that translates these inputs and outputs into environmental loads. So for this work, we use the environmental footprint method. This is recommended by the European Commission for comparing impacts between processes and products. And as you can see in the screen, this method allows us to evaluate 16 different environmental impact categories, not just carbon footprint, but also others that can be really relevant, as I'm going to discuss in the next slides. For example, resource use of fossil materials, particulate matter emissions, or for example, also land use. And the final step is the results analysis. This allows us to identify the hotspots of the process and also propose sensitivity assessments to try to find better solutions and to reduce the environmental impacts of the process. So here, this will be the environmental profile of the conventional multi-cylinder dryer. As you can see, there are three main hotspots that account for most of the environmental impacts of the process. So in order of contribution, the biggest one across most of the impact categories is the consumption of thermal energy. This is mainly related to the combustion of the natural gas and also its production. This is the blue bars. After that, we have the electricity consumption, the orange bars, and finally the water use. So if we focus on the climate change category, which is basically, this basically gives us the carbon footprint of the process, we can see that the total emissions associated only with the drying stage, this is only related to the drying stage. These are about 214 kilograms of carbon dioxide equivalent per ton of paper produced. And out of this, 168 will come directly from the emissions due to the combustion. So these are the ones for which a paper mill would actually pay for. But of course, it is important to take into account that the remaining 46 kilograms of carbon dioxide equivalent come from background processes, as for example, the electricity production, or as I said before, from the natural gas production. So quantifying these background processes, it is also essential if we really want to achieve this whole net zero value for the complete value chain. So it is also important to mention that these values mean that the current benchmark for emissions in a paper mill are actually exceeding if we are using combustion technologies. So as you can see in this slide, when we use the superheated steam drying technology, we can reduce energy consumption, as my project partner said before, but also as a result, of course, we have a reduction on the carbon footprint of the process. So with this system, we can go from 214 kilograms of carbon dioxide equivalent down to 41 kilograms, taking it here as a reference case, the European electricity mix production. And this remaining value, it is important to say that it comes entirely from the upstream electricity generation, so not direct from the emissions at the mill, not from combustion processes or something like that. So what I think it is also interesting is that by fully electrifying this heat generation, we can move toward very much close to these zero emissions in the drying stage if we are able also to use renewable electricity. So in fact, when we take the Swedish electricity mix as an example, we see that this value of 4 kilograms of carbon dioxide equivalent is pretty close to zero. But we also need to keep in mind that even though we are reducing the carbon dioxide emissions of the process, the use of these new technologies can have bigger impact on other environmental categories, as you can see in the graph at the right. So, for example, using more renewable electricity or sources, this usually means, for example, higher land use, or as you can see, also higher mineral resources consumption, if we compare it to the conventional technologies. So, while it is true that current priorities push us to focus mainly on emissions, it is also important to understand and quantify how these choices affect also other environmental areas. And this is something that we are also addressing and analyzing under the SteamDry Framework project. So that will be all by my part. I will be very happy to answer any of your questions if you maybe have one.